because I've sort of done a little more research on the AstraZeneca vaccine. It's all of an evolving thing. And there is really interesting information. I mean, interesting. AstraZeneca, they're out of Oxford, and the way they've handled it.
I'm sorry, can we start the recording now since we're getting some information, Louise?
Yeah.
I have already.
Oh, okay, sorry.
No, that's all right.
And it's very interesting. The whole thing about colonialization has become important in the distribution of the AstraZeneca vaccine. And that's why I had to go back and do my research. Jamaica was or is a colony of Great Britain.
Yes.
South Africa had that that history, and they're not as worried about getting the United States as a market. So they haven't been tested all that much here in the United States, gone through FDA testing, but they've been really sloppy. They did this thing with the second dose.
Claudia, are you talking about AstraZeneca?
Yeah, I am.
Okay.
And they're one of them that is one of the infection ones that I wasn't going to start this way, but I'll wrap this up. But and there's Johnson and Johnson is the other infection one, and but AstraZeneca, they're 2 dose, and J&J is 1 dose. But they messed up totally on what the second dose was.
Really?
They didn't even know it until they opened it up and realized that people were getting the wrong amount. And I mean, the bookkeeping has been really sloppy. But that being said, it probably is a good vaccine.
I don't know what I'll have to ask my sister. I think she got Moderna.
Yeah,
I think my stepmother got Moderna.
Good.
I think.
Yeah, I did too, but I've only had 1 shot. I'm curious, does 1 shot do anything for me?
Well, okay, I wanted to address that. I don't know what this means that there's so few people, but why don't we just start?
Yes.
It just happens. It happens to us all the time.
All right. Well, because I kind of felt a really good vibe even over Zoom, but I have a couple concepts that I want to go over. I'm going to start again with my terribly written chart.
That's good. It's good.
I can
But
read
just to
it.
say that a virus is made up of genes. And usually genes are DNA, made out of DNA. The building blocks are DNA. But in a lot of viruses, for some reason, they're RNA. And they get, and in a little later, I'll talk about that, but let's just think about genes. And basically, the virus, it can't work without a host cell, like a bat, or a human being. And but to get into the cell, it usually has some sort of protein on the outside that binds to a receptor on the host cell, or in this case, the human cell. And I saw somebody do a computer game where it is the pattern that it locks onto, or the conformation, the 3-dimensional structure. And if it fits, it fits. If it doesn't, it doesn't work. And I'll get into that a little bit later. But when we talk about the virus getting into the cell, it has to connect with this receptor. Now, we've been talking about immunity with this virus. And I'm sure you remember with HIV infection, immunity was always talked about with T cells. And I don't want to go into the whole biology of immunity, but we have to remember that immunity really has two pathways. One is the antibody pathway, and we talk about it coming from B cells. The other is the cellular pathway. And and HIV affected the cellular pathway. Actually, its receptor was on T cells. So it killed T cells. And that's why people started getting certain really bad infections. And that's why it started out being called acquired immunodeficiency disease syndrome, because at first people were presenting with infections, and the infections that they presented with were the infections that this cellular pathway treats. Whether or not that is relevant to coronavirus is only being uncovered. And let me see. So now this is kind of a human cell. And, oh, I know what I did want to say.
Claudia, quick question.
Yeah.
Are B cells and T cells white blood cells?
Yes, they are.
Okay.
They're part of the lymphoid system.
Okay.
And B cells live in lymph nodes. And T cells live in the thymus gland, which is actually in the neck. And that's how it got the name T cell. And this is going to go to the work you did, Jean. The T cell pathway, or the cellular pathway, basically treats infections that are more from parasites and tuberculosis. And that's why people with AIDS got all sorts of weird parasitic diseases, because the cellular pathway was killed off. Now, I'll get back to this, but basically, remember the direction is that in a usual cell, a eukaryotic cell, from the higher level cells, the genes are in the nucleus, and they're usually DNA, and there are building blocks that make that up. They're called nucleotides. And from the DNA, one makes messenger RNA. And the DNA, it's a double helix. It splits apart. It's got a code based on the sequence of the nucleotides. And it codes for, and so a copy of it is made, and that copy then goes out into the cytoplasm. And from that copy, we make proteins, and it uses the code from the genes. So it doesn't transcribe all of the genes, just the gene of interest. And then you get a protein, and a protein is made up of amino acids. And it's proteins, and then they, based on the amino acids, they fold up into a conformation or a three-dimensional structure that has certain activities, but also gets recognized in this key and lock thing, or that even the antibody recognizes. And a mutation occurs from the genes and the DNA when the cell divides and replicates, and a mistake is made in that replication. Now, what the virus does is it hijacks, it's not really a cell. It's made up of genes that aren't even a full complement of genes, but it's enough genes to take over the nucleus of the host cell and hijack it to do its work. And the mutation and part of the and really the goal of the virus is not to kill the host, but to have a host that will live long enough to replicate it. And because if you kill the host, it can't replicate. So it's not really trying to kill you, although hijacking, your genetic activity ends up killing you after a while. And a mutation is when in the replication of the genes, one of the nucleotides, a mistake is made. And then that ends up with a mistake in the messenger RNA, that ends up with a mistake in the protein. And the mistake will change the three-dimensional structure of the eventual protein product. Now that could either make it a better protein, so it's the survival of the fittest, or a worse one. The worst ones don't live, it's the better ones. And we think that a lot of it ends up making the spike protein bind to the receptor in a more effective way. And we can test that a few ways, but the words we use is in vivo. We can see what's happening, and that's in the person. In vitro is in the test tube. All right, so remember we talked about that the different vaccines, that there's three types. One is mRNA, and only in the United States right now, the FDA has only approved mRNA based vaccines. And Moderna and Pfizer are mRNA, and it's the mRNA not for the whole virus, but mRNA for the spike protein. And you end up making that protein. It ends up in the blood. It's recognized as a foreign body, and the body makes antibodies. And the antibody recognizes that spike protein on a virus. And it does it again a little bit like a lock and key, or key and lock. And it makes it so it covers it up so it can't bind to this receptor and it can't replicate. Now, we think that it's mostly the antibody pathway, but there may be the cellular pathway that is important. That part we don't know. And if you recall, the second type of vaccine, are ones that use a virus. In the J&J one, which is probably going to be approved next week by FDA, it is a respiratory virus called adenovirus that they've altered genetically to have this coronavirus spike protein. And you get it injected into you, and you literally get an infection from that virus. But you'll develop immunity to that respiratory virus, but that's not the goal. The goal is for the spike protein for coronavirus. And so the question, and if you've seen the difference in efficacy, the Moderna and the Pfizer, they're really high. They're like 95%. And with the J&J and probably the AstraZeneca, which is of that type also, it's lower, but it seems to protect you from getting serious disease. And what we don't know, it probably stimulates the cellular pathway more than the mRNA ones, but we don't know. And that may be related to what we're calling durability. And these cells are memory cells. And so they remember whether or not you've ever been infected with this. And then they, and so what we don't know, like the mRNA ones, which is the one I took, and I decided I wanted, has wildly high efficacy, but we don't know how long it lasts. And theoretically, the ones that use infection may last longer, but again, no one knows. And then finally, there's a third one, which is still in the pathway where they use cell culture, and they're making this. They're having the cells in the test tube, or in these big vats, actually make the spike protein, and then they purify the spike protein and they inject that in you. And so those are the three platforms, and no one knows which is going to be the best. And it's probably ending up that, well, anyway, I would like to try to, I want to talk about prevention, but there's a couple of topics, and maybe I'll just be able to do one of them. But I wanted to talk about what exponential growth means, because it's really important, and it's kind of it could be a hard concept, but it is where Trump really messed up. And it's also why you can tell your kids or grandkids why they should take math. It's where all that algebra comes into play. I wasn't terrible at math, but I'm more somebody that can tell the concept, and can't do all the math. But I just want to talk about exponential growth versus linear, and why you don't want exponential. And so an example of linear growth, and you keep seeing these charts that they put up. And Anthony Fauci loves to, he'll talk about things, and he'll talk about the slope of the curve, and whether it's gone from linear growth to exponential growth. So here is the analogy that I've heard. In linear growth, it would be, say something was increasing by 50,000 infections a day or a week. But anyway, a given amount. That's linear. Exponential, exponential is when it's growing leaps and bounds. And this is how it works. I'm going to give what's called the lily pond example. And think about, and so the idea is, if you get infected with the virus and then I infect somebody else, are we having linear growth or exponential growth? And when it moves into exponential growth, that's bad. So I'm going to talk about exponential growth, and I'm going to give a lily pond. So think about a lily pond that has lily pads, and a lily pad makes a new one every 24 hours. So each lily pad is making a new one, and it takes 24 hours. So in one day, it goes from 1 to 2. and then it goes from 2 to 4. And here's where you really start to understand what happens with exponential growth. Is think about a lily pond that is half covered yesterday. When is it going to be fully covered? Today. So you go from, because each lily pad is reproducing only 1 to 1, but it's doubling each time. And so you go from half to the whole thing. And that's why, and so it's only when the replication rate is 1 to 1, but that's exponential. And that's why it was letting it in and letting it take root was really the big mistake. Because then once it's in the population, you have a load that is going to cause transmission. And when you and you could have the same transmission rate. I mean, a person is going to transmit it to the same extent, but if there's this many more people that have it, then you start to get this exponential growth. And that's why it's been so bad. And the slope of the curve, all those curves they're showing are telling you whether we're in linear growth or exponential growth. And so when they're showing you these curves in the newspaper or on television, and they're saying, well, geez, it took us, from such and such state to such and such state to get 50,000, but now we're getting, 100,000, 500,000. It's because we're in exponential growth. All right. Now I want to talk about prevention. And this is a respiratory virus. And with viruses, we talk about the portal of entry, or the door that it gets into the body. And in respiratory viruses, it's through the nose and the mouth into the respiratory system. And the reason it does that is because the receptor that it binds to is in the lungs. And HIV binds to actually a T cell, which is in the blood. And that's why it requires blood products or secretions to get in. So, and I'm going to say this, but if you think about it, the mask is not unlike, the mask to coronavirus is not unlike the condom to HIV. It's exactly the same. And it's just preventing the virus from getting to the place that it needs to go. And that's why it's become such an important prevention strategy. And same with, the condom with HIV. And then, and you can look at and we can maybe at some time talk about different mask strategies, but really all you, to transmit it, it's going to come out of your nose and mouth, because that's really the respiratory system. And so you need a mask. It only really needs to cover this, but that's what it needs to cover. Now you can receive it through the eyes, but you're not going to give it to somebody through the eyes. Now, so the mask is really important. And at first we thought it was just important from you spewing out virus for the population, but now we're realizing that it prevents us from getting it. And then I want to talk about, well, what do we spew out? And we spew out droplets, or spew out water that has virus dissolved in it. And when it's part of the upper airway, when you cough or sneeze or even talk or sing, singing is just horrible for it. You are spewing out stuff that's coming from the upper part of the airway, the trachea, and it's big particles. They're called droplets. Now, when it goes down into the lung, it's a much narrower airways, and so it turns into what we're called an aerosol. And the droplets are big, although we don't really see them, but they're big. And they end up falling to the ground, and they fall on surfaces. And that's why you need to end up washing your hands and that kind of thing, because it's basically dropped down on the surfaces. When it's the aerosol, so the words you'll hear is droplets and aerosol. And an aerosol just means it's really, really little tiny things, and it's in the air. And this is where ventilation is a problem. So if you don't have good, if it's just droplets, ventilation isn't that big a deal because it just falls to the ground. But if you have the aerosol, it's a big deal. And you need good ventilation that's going to circulate and filter these little tiny little droplets. And that's what's going to be hard with like Church and Ocean Park reopening, because it's the aerosol. And some viruses don't do an aerosol, but coronavirus does. Now,
can I ask you something, Claudia?
Yeah, please.
If most people get the shots, both shots, and then we still have to worry about the people who don't get the shot for whatever reason, they don't want to get it. We still have to be careful, right?
And this is why I want us to have these conversations, because this is all evolving and we don't really know. We're hopeful, and they are talking about, if you got two people that are vaccinated, just get together. The hard thing is these variants, and whether or not the vaccine protects you from the variant. And so the variant that's coming from South Africa, it changes the conformation of that spike protein perhaps so much that the antibody that's generated from the vaccine doesn't recognize the variant, and therefore it doesn't protect you. But that, in the last week, since we talked, I think there's some recognition that we've got to give people hope. And yes, that, maybe just there's going to be some amount of, really good protection from the vaccinations. And if people enough people get the vaccination, it will be safe. It's just that if you have somebody in the herd, so to speak, who has the variant, they might still be able to infect you if the vaccination that you got doesn't protect you against that variant.
This is leading up to a question I had, Claudia. If I get the vaccine, and I am exposed to COVID, but I obviously don't get it, can I give it to somebody else?
And again, those are the studies that they're doing right now.
Okay.
And so what I found out, between last week and this week is all of the endpoints in the studies were about getting severe disease or even mild to moderate disease, but not whether or not you're infected. And you could be infected and not get disease, but be able to transmit it. And that's what they
Can
don't
I
know yet.
transmit it when I've had the vaccine?
Yeah, yeah. And so, well, we don't actually know that. The studies, when they tell you efficacy, they're not telling you whether or not you can transmit it. They're telling you that you're not going to get sick. And those studies are being done right now. And so the concern is that you could still get it and transmit it. But it's looking kind of good. It's looking like maybe, what it does is it reduces that viral load. And you're not gonna and like the UK virus or variant, it does such a good job docking in that lock and key thing, and that's what makes it more transmittable. And it takes less of a viral load to do it. And so you wouldn't be. So I guess this gets to Fred's question. People that are vaccinated aren't going to be at risk. Even if you can transmit it back and forth to each other, you're not going to get sick. But you could transmit it to somebody else who hasn't been vaccinated. Maybe, but they don't really know. Okay. Now, one thing I do want to say that's really interesting is that out of the people who have gotten the infection, get this, a full 90% have occurred indoors and only 10% outside. And that's a big deal. And if that holds up, having church or singing outside, we're just going to have to find outside because that's a huge difference. And then, you can see the social distancing. I mean, if it's one guy describes it as swapping air. And the idea is not to swap air with somebody. But then you can see if there's an aerosol, that's why ventilation is so important. And of course, that's what's becoming a big deal in schools. All right, I want to talk a little bit about testing. And that's going to become more and more important. The PCR testing, and maybe I'll talk about that another time. I was going to tell you what PCR was, but that's it's something to know, but I won't do it this time. But it is set up, and it has to use laboratory equipment, pretty sophisticated laboratory, and it looks for the virus gene, okay? And let me see what I want to say about that. And then, and that takes sending it away to a laboratory, and it takes a while. Now they're doing it at the airport, but it takes about 3 hours. The other kind of testing, the rapid testing that we're going to be able to get at our homes, actually detects the spike protein. And it's what we call an antigen test. And an antigen is always a protein, and the antibody binds to an antigen. So there's the PCR test is testing for the genes of the virus, and then the antibody test. I mean the rapid test that you can do for schools, you can do it at home. It's really looking for the spike protein, and that's going to become really helpful. And then I guess the last thing I really want to say is they're talking about genomic surveillance, and that's to look for the variants. And what they're doing is actually sequencing the whole gene of the virus and seeing if there's any changes in it. So, and then just real quickly about treatment. I wanted to say something about hydroxychloroquine and where they went really wrong with that. Hydroxychloroquine works by interfering with mRNA, making a protein. And it does it in our parasites, and that's why it's a malarial drug. Well, they were really stupid because human cells aren't parasites. And, you know, so it's not going to work. And it didn't. No, treatment is when you hear about the monoclonal antibodies, they're literally injecting the antibodies that you would make to make the spike protein covered up. So it's a way to inject, and the antibodies, when they say monoclonal, it just means they've made clones of cells that are in cell culture in the test tube make it. When they talk about convalescent serum, they're taking it from patients and they're getting the antibodies that a patient made. So that's how treatment right now is using these monoclonal antibodies. It's over and over and over again, trying to get an antibody to that spike protein. That's, you know, the theme. Now that Trump's gone, and the real push is to do what, I'll say this quickly, this is a bigger subject, but to get the antivirals that was developed, that kind of thing is what got HIV under control. And you interfere with this whole process of a cell replicating a virus. And real quickly, you've maybe heard the term reverse transcriptase. It's just, I won't go into it. It's just that you've got to interfere with that replication. And antibodies were never to be able, it didn't work with HIV, but they interfered with that whole replication process. And that's what they're looking for with coronavirus. And it'd be nice to get that so that you could take it as a pill, whereas these antibodies, you know, require an IV. So does anyone have any questions? Yeah, Jean, I can't hear you.
Okay, so I have several questions actually.
All right.
One is when a person who has COVID symptoms is being tested, how do they know that it's a variant? Do they actually see?
They don't know, Jean. They don't know. And so what Walensky at the CDC has set up, they're just testing for either the gene of the spike protein or the antigen. To see if it's a variant, they have to send it for sequencing. And Walensky, we haven't been doing that. And that's being ramped up. And so that when they say genomic sequencing, that's how you test the variant. And it's the actual gene.
Right, but I mean, we hear reports of the variant is running through California.
It's only when what they did sporadically is that university labs can do the sequencing, and they so they would send samples of the virus. It's separate from the testing. They literally have to take, because the testing is only PCR, which I can go into another time, is only looking for the single gene of and it's only a little part of it through PCR of the spike protein. To see the variant, you got to sequence the larger part. And that's actually a different procedure.
Okay. And then the other, I'm going to ask one more really quick. The mistakes in replication, where you get those errors, is that caused by mistakes that we make as humans in taking care of ourselves, nutrition, exercise, that kind of thing, or is it just random?
So,
I mean, should I tell
yes and yes, but I'll say it simply. When our cells divide, they replicate the DNA. And they use something called DNA polymerase. It makes a polymer. It's long. There's a certain error rate with that sequencing. And with that error, you get a mutant. Now, that mutant can be important or not. In our body, you get cancer from that. That's precisely how cancer arises. And we use this cellular system. I mean, this is where it gets fun talking about this, honestly. The cellular system then recognizes on the surface of the cell that it's slightly changed, and that's immune surveillance, and it gets rid of the cancer cell. Or in a cell that's infected with the virus, it sees that there's a change in the cell. It gets rid of the cell. And so that's where good diet and being healthy keeps your immune system active. And that's what your immune system is for.
Great, thank you.
So I had a question.
I think Daria had her hand up, and then Gina.
Okay, I have two questions. My first question is sort of based on Fred's question, which is, if 51% of the population is vaccinated, does that keep us safe? That's my first question.
Well, if you notice, Anthony Fauci keeps getting himself in trouble. And, you know, he keeps saying what percentage of the population needs to be immune in order to get what they're calling herd immunity.
Right, that's right, yeah.
And you can get herd immunity either by supposed natural infection, which is getting the virus, which is what that guy Atlas that was, advising Trump thought Trump should do. And that's literally what he was going to let us do. The problem with that is you replicate and then you come up with variants. So then you never get herd immunity. But you can also get herd immunity acquired. And one of the acquired ways is through the vaccinations. And so there's nothing from a math point of view, there's nothing about being over 50% that's important. It's about being over, he's saying up to 70, 80%. But honestly, that question is not known.
Okay, thank you for that. And then my second question is what you call swapping air with other people, the way in which we quote unquote give the virus to other people?
Yeah, you're only going to get it from air that comes from somebody's respiratory system. And if it comes from the upper part of their respiratory system, it's going to be a droplet. If it comes from their lungs, it's going to be an aerosol. And it's going to, and whether, if you get if they are able to successfully transmit it to you, it has to do with the viral load in that air. And so if it's brought down, then you're not as likely to get it. And that's what being outside does, or it seems to be what the vaccination does, or it seems to be what children, for some reason, don't have as much, as dense accumulation of particles in their lung air.
So you really just, that's what the social distancing is that's why that's so important. You just simply don't want to swap air, period, end of story.
Yeah, and and it really is like the condom. You don't want to swap semen, so to speak. You don't want to swap air. It's really not hard to think about once, you start thinking about it that way. Yeah, Daria.
So I was speaking to a friend of mine yesterday, and he had COVID about 2 weeks ago, and he's probably around 62, 63. And what he'd said was that there are people who get very light symptoms, people who get more severe, and then he says 1% of the population gets the fatal symptoms where they die.
Mm-hmm.
Is that true?
That is true. And the fatal thing that they die is the second part of the disease that I was talking about, where the inflammatory, the immune system gets overactive and it literally starts attacking your lungs. And that only happens in a small subset of people, but it's people that are older and with pre-existing diseases. But then what Gina is describing is with a regular infection that isn't this lung thing. There are longer lasting chronic symptoms. And, this is, eventually, it'd be nice to, I'd like to collect these stories. We should hear how it affected you, Gina, because we're really only learning about this disease, and we should write them down, keep a journal, a little compilation of what's happened to people. Yeah, Jean. Well, you're muted.
What about being infected from surfaces? I haven't heard very much about it. I still, wipe everything down after I come back from any kind of market or store. The mail, we don't.
It's turned out, it's got at the beginning, they didn't think you needed to wear the mask. They thought droplets that would fall down to surfaces would be far more important. And it turns out this aerosol and swapping air is much more important. And so in a way, surfaces aren't as important. I don't want to say that they're not important, but they're not as important as washing, the mask is the most important, and being outside and then washing your hands. I really use a lot of hand sanitizer when I'm out and about. I guess I must confess, I don't worry about surfaces that much.
Yeah, I just, I went with Gary to the doctor, and I avoided touching the doorknob. I asked him not to lean on the counter. Is that not important, or should I keep it up?
Oh, it is important. And, if anyone's been, I haven't been going out that much, but I always push the elevator buttons with my elbow.
Me too.
And I try not to have, because it's going to be from your hand.
On doorknobs. I don't.
Yeah. So, but that's probably from somebody that would have touched their secretions from their face and then touched the button. I even was going to the, like when you go into the a parking garage and you push, to get the ticket. I've even started to, you want to not touch something that people repetitively push. So those kind of surfaces. And then and they're going to be testing this more and more, but it's how long some about the virus lives on a surface. And they don't, they think not very long, but they don't know.
Okay, thanks. This is great. This has been wonderful.
Could you talk about contact tracing and what the process of that is and what it is? Just, I'm not 100% clear on it, but I do support it.
It's fun to do in a way.
Oh,
And I don't know the actual procedures. It's sort of, it falls in that public health realm. But I mean, you know, you know, it started with, in a way, a long time ago with tuberculosis or with HIV, and it's to try to figure out, oh God, and you can't have too much. The idea is to figure out who you got it from. And, you know, in a way, Gina's question potentially could be answered by that. The thing is, it can't be too common because then you can't ever know. But they literally contact your contacts, test your contacts as to whether they had it. And then by process of elimination, they figure out who you most likely got it from. So I'm not going to be real good at telling you exactly how they do it. They use, but they have you make a diary and they have you talk about where you went and who you were close to. And then they go test those people. And then they see which of them were positive. And they probably do that antibody, which is, you know, circulating in the blood.
And
So
Claudia,
it sounds like,
they also contact the people that you saw after, but before you knew you had COVID. So you might have gotten it from somebody, but then been around other people and you might have given it to them. So some contact tracing goes further.
Yeah, and so, Jean, I'm really glad you said that. And so the words, to be precise, if you've been exposed to somebody, but you don't know if you have it, the word that they use for that is quarantining yourself. And you quarantine for, I don't know, something like 14 days. But if you get it and you know you have it and you could transmit it, the word is called isolating yourself.
Huh.
And so you quarantine when somebody, you know, say through contact tracing, they say you've been exposed. Those people are quarantining. And that's what you're supposed to do with either exposure or international travel or that kind of thing. But if you get it, you isolate yourself. And obviously, isolating yourself is much more important in a way because you know you have it and you can transmit it. Anyone else have another question?
Yeah, I'd sure like to know what happens in my body after I get a shot and why you have to wait 2 weeks after a shot and you know, what's happening?
It's the developing immunity. And there is a whole process by which proteins or antigens are presented to the different lymph cells, the B cells and the T cells. And it actually chops, this is so getting, I haven't thought about this in a while, but it chops it into little pieces, the protein.
Well,
And then you develop plasma cells that generate an antibody based on the structure of that protein. And then you have the antibody. And it's boosted. Okay, this gives me a chance to say something I meant to say. But it takes a while for that system to get started. And then when you give the second one, it just revs it up. And they think that it revs it up so much that it's going to make it more effective and it's going to make it last longer. And so they're playing around with the time frame between the first one and the second one. And then this is what I wanted to say. The mRNA vaccines, for the mutants, this is the cool thing. It's synthesized in the test tube. So they can make any sequence they want. So with the variant, all they have to do is change the sequence that's in the vaccination.
Good.
So pretty soon, the vaccination is from Moderna and Pfizer is going to have the mutant sequence in it. And that's how they're going to keep. So we may need boosters, not only to rev the immune system up, but to deal with the mutants.
Gotcha. That's what I needed to know, that stuff. Thank you.
Are we going to end soon or?
Yeah, we could end and, you know, let me, I mean, maybe you could feedback to Jean, you know, if this is useful to you and how often you want to do it. I mean, I feel like there's going to be updates and we're going to be able to revisit a lot of these questions and have better answers. And then I would love to get it so that people who've either gotten the virus or gotten the vaccine tell their stories.
Mm-hmm. That would be a good idea. So we can talk about that, and maybe I can send out an email, see how many people are interested in an update. Send it to the general population because some people haven't been here yet. So this was very, very useful, very helpful.
Yeah.
Lovely.
You know, I think, but I could be wrong, that you're going to be able to now watch, I don't know, the news about this and have a little better idea because of the terms, what they're talking about. But I'm not sure. You can tell me.
Yep. Yes. Thank you.
So.
Yeah, thanks. That's a good idea.
That's wonderful. Thank you.
All right. Thank you guys. See you all another.